Dear colleagues, it is a great pleasure for me to participate in the conference dedicated to this great event. The ideas and approaches inspired by Aharonov and Bohm 50 years ago go far beyond the initial setup of quantum mechanical scattering of a particle on a tube enclosing magnetic flux lines. In this talk, we consider the influence of topological defects on the properties of quantum matter. Topological defects appear as a consequence of spontaneous symmetry breaking. If a topological defect is characterized by non-trivial first homotopy group, it then possesses some flux, and we shall study the effects of this flux on the matter which is quantized outside this topological defect. In the first part, we consider quantum matter in the framework of non-relativistic quantum mechanics, the effects of quantum mechanical scattering will be studied, and in the second part we shall consider quantum matter in the framework of relativistic quantum field theory, the vacuum polarization effects and the effects of finite temperature will be studied. Our consideration is quite general. As it is known, the Aharonov-Bohm effect is periodic in the value of the flux, and it vanishes for some quantized values of the flux. So it is necessary that the flux, the gauge flux, will not be equal to this separate quantized values. And maybe therefore the application of this general consideration can be in cosmology and nanophysics. That is, in cosmology we consider the effect of cosmic strings on quantum matter on the matter on quantum mechanical matter and in quantum field theory, and in nanophysics we consider the effects of disclinations on the electronic properties of graphene. Okay. So spontaneous symmetry breaking of local symmetry, the simplest model includes gauge field and scalar field, and after the spontaneous symmetry breaking, the scalar field X scalar attains mass, and mh, and gauge field attains mass mv. And the topological defect of non-trivial first homotopy group is the Nielsen Abrikosov-Nielsen-Olesen vortex. It is a line defect, line structure, and you see this function tau very fast goes to its asymptotic value, and this is the region of spontaneous symmetry where the spontaneous symmetry breaking occurs, and outside the defect and inside the defect, the symmetry where tau is almost zero, the symmetry is conserved, is exact, and the region of topological defect is characterized by the gauge field in the direction of this string and the stress energy tensor. This is, for brevity, some simplified case, consider when gauge field mass and Higgs scalar mass are equal. In general, when they are different, there are superconductors of first and second kind. But what we would like to emphasize another point, that the appearance of this stress energy tensor is a source of gravity according to general relativity, yes? And so the Einstein-Hilbert equation, and in the region where of this topological defect also scalar curvature is non-zero, and it is convenient to describe this defect in terms of global characteristics, which are at least two, that is gauge field flux and linear energy density, or tension mu, and this integration of a transverse section of this defect, and it suffices to integrate over the of the core of the defect, since otherwise these integrands are zero. So flux is related to inverse coupling constant of Higgs to gauge field, and tension is related to the squared mass of Higgs field. And in principle, the third parameter is the ratio of mass of Higgs scalar to the mass of vector field. Now, the metric can be calculated using this Einstein-Hilbert equation, and also outside the string, it is flat, it is non-Minkowskian, because the surface which is transverse to the string is to this vortex is a surface of a cone with the deficit angle. This is deficit angle equal to 8 pi g mu. G large is the gravitational constant. So these topological defects in the context of cosmology were introduced were considered first by Kibble and Vilenkin, but much more earlier they were considered as conical spaces by Firth and others. And
what motivation did they have to study such a thing?
What, please?
What was the physical motivation?
Whom?
Unpublished guys and published guys.
Yeah, they just considered cylindrical symmetric solutions and most general solution, and found that the most general cylindrical symmetrical solution there are such conical spaces.
Oh,
and
basically exact solution itself. Right?
Yes. Okay, so cosmic strings in cosmology, they are characterized by very small this deficit angle. You see this value, and cosmic strings may have very interesting consequences, and among them the double image of the object, which is directly after this cosmic string. But we shall be interested in the effects of cosmic strings on quantum matter. So quantum mechanical scattering on a cosmic string of a test particle on a cosmic string was considered in these works, and I shall list the results, the scattering solution to the Schrodinger equation, and the motion along the string is free as for Aharonov-Bohm effect, and so it's the solution, scattering solution. It's asymptotics of the solution. Yes, here note that this is constant of this coupling constant of this test particle to this gauge field of the string, which is different from this coupling constant of the Higgs scalar to the gauge field. And now this is the asymptotics at large R. and this is wave outgoing spherical waves in 2 dimensions. That is why the square root of r in the denominator. This is spherical outgoing wave, and the coefficient before this is the scattering amplitude. But first, the first term, zero order term in this asymptotic expansion, it is given by finite sum, where L integers which are in this range. For the case of Aharonov-Bohm scattering, when tension is 0, there is only one term, and you see this is a plane wave with some distortion, and this distortion is a consequence of the long range nature of scattering for the Aharonov-Bohm potential. But in this case, when there is a conical space, this long range nature is amplified, and so it is this term is how to say some distortion of this initial incident plane wave. Now, what is the expression for this scattering amplitude? Two parts independent of R, C, and dependent on it, and this first part, which corresponds to the case when we neglect the transverse size of the string, and the sum, infinite sum, can be taken, and this is the result, and it diverges in 2 directions, symmetric to the direction of forward scattering. And in the case when mu goes to 0, it goes to this expression goes to the scattering amplitude obtained by Aharonov-Bohm for scattering on an idealized magnetic string. And the second term is not, the sum isn't taken in general case, and it is given by this alpha n is given by this relation. But fortunately, we see that as k goes to 0, this term can be neglected, containing the dependence on the size of the string, and the idealized string is working. And in opposite case when k goes to infinity, on the contrary, f0 goes to 0, and this term is essential. And namely, in this k goes to infinity limit, this sum can be taken, and it was so. This is differential cross section in the low frequency limit, yes, and this is the differential cross section in the high frequency limit. You see, it was some work to get this formula. Even the number theory methods were implied, and you see again this finite sum, and with this L integers L line in the finite range, the same as was for this incident wave, for incident wave okay. How to? Okay, so in the case of vanishing tension, there is only one term, and so the differential cross section in the high frequency limit goes to the classical scattering of a point particle on a tube of finite radius. But as long as you have as long as you have some finite number of terms, you get the interference, and you see that then the dependence on the gauge flux will survive. But before telling about this, I just show you this is classical scattering, simple classical scattering. This is string orthogonal, surface orthogonal to the string. The classical scattering, the angle scattering doesn't depend on the impact distance. So you just write parallel lines on a conical surface and get these pictures. So as deficit angle grows, 2 pi eta is the deficit angle, grows, this scattering angle grows more than pi by p, becomes more than pi by 2, and goes to value of pi, and then the picture looks like this for eta more than 1/2. It looks like this, and then the scattering angle diminishes, and again it is periodically. Here it is written how it is changing. Certain eta is for general for the whole range of values which can be have sense for the nanostructures, for nanocones. But for cosmic strings, certainly eta is very small, as I showed before. And for negative eta, you have such a picture. And you see now to this formula for quantum scattering, this number of finite terms is different in this region. This is region of cosmic string classical shadow, and this is this region of double image, of classical region of double image. So, out of this region, out of these regions, the number of terms is odd, and inside this region it is even. And here it exceeds by 1, this number, and here it is less by 1 than in this region. If we start with negative eta, we have here one term, here 0 term. For this case, it jumps to 2, and here 1, and then again, as you change this parameter eta, it is jumping by 2, either in one or another difference. So I give the explicit formula for this case. You see, there are 2 terms, and there is this interference, and there is in the high frequency limit, you have the dependence, periodic dependence on the value of the enclosed flux. And for scattering in the forward direction, you get this formula. But this is for differential cross section, and for total cross section, this dependence disappears. It's doesn't depend on the value of flux. So the conclusion to this part of my talk, that the high frequency limit, the differential cross section, depends on the periodically on the value of the enclosed string flux, and this is contrary to our expectation that in the high frequency limit there will be some quasi-classics, and there will be smooth tending to classical limit. Now I have 1 minute, but I just have time to list that This in the framework of quantum field theory for almost 20 years were considered the effects of the enclosed flux on the properties of quantum matter, vacuum polarization properties, and it was found the relativistic quantized field are either with spinless or with spin, and there was found that enclosed flux induce vacuum energy density in this matter, so it may be called as a Casimir-Aharonov-Bohm effect, and in one paper this terminology was used. Also, some current circulating in the vacuum around the flux was found. Interesting results are for quantized spinor fields. Then the charge is induced in the Aharonov-Bohm manner in the vacuum, and so it's like a charge fractionalization, but by the Aharonov-Bohm configuration. Charge, angular momentum, spin, condensate, and more recently we considered some temperature effects, and here you see the effect of this deficit angle was considered under some restriction by these people, but I shall just have time to show the result for the vacuum current, which is induced by the cosmic string. It has this periodic dependence, yes, on the gauge flux. Yes, this formula is given for massive quantized scalar field in d plus one dimensional space-time, but by this cosmic string, it's generalization to d plus one dimensional space-time. And then, since this vacuum current can be considered as some macroscopic quantity, and if the Maxwell equation is valid, then this current then this current leads to the inducing of the magnetic field, real magnetic field, which is enclosed in this cosmic string. And so, if the mass of quantized field less than the mass of the Higgs scalar, which forms the cosmic string, then the string is dressed. The cosmic string is dressed by vacuum polarization effects, is dressed by the magnetic field. Okay, thank you very much. I have not told you about the nanophysics application. I just say two words that in carbon nanophysics, this deficit angle can be rather large, multiple of 60 degrees, multiple of p by 6, and so these effects which were for very small deficit angle, they can be, in nanophysics, they can be for very large deficit angles. Thank you very much.
What is the observational evidence for cosmic strings?
Can you repeat the question?
Repeat. The question was my attitude to the evidence of cosmic strings. You see, there were different aspirations, and even some years ago it was claimed that the cosmic string was found by this double image, but it was. No, Zurich it was earlier, but I say that some analysis of Sajan and others, but it was withdrawn, this claim, and unfortunately now there is no experimental, how to say, substantiation of the existence of cosmic string. That is the situation, to my regret, certainly.
Well, let's time